right, hello everybody. My name is Herke van Hoof. I'm a associate professor here at the University of Amsterdam. And today, in the context of this workshop, I'd like to talk about reinforcement learning for real-world network infrastructure. To kind of sketch a bit of context for this problem, of course, we've seen super exciting results in reinforcement learning in... Oh, it's not on? Maybe I'm just too far. I think it's on. Oh. Close enough? Okay. All right. Does that work? Yeah, I think it works. All right. So in the past decade, we've seen this very exciting results in reinforcement learning. However, right, these are in kind of these very constrained systems, right? So a lot of it is in simulated environments or games or maybe kind of robots, simulated robots that are working in isolation somewhere. And there are, of course, many other more like real world applications where these algorithms can have an impact, where we kind of don't maybe yet see this breakthrough result, right? So it's good to ask ourselves, like, hey, right, what is needed to actually, right, make something useful that can be used in those domains? And I think, right, this is maybe also the topic of Diederik's talk, right, kind of is about some of these obstacles, and maybe I'll address a couple of other ones. So, right, there are many other domains in which learning to make decisions would be useful, but these also offer additional challenges that maybe we're not usually addressing in our research. And in particular, today I want to talk a little bit about the AI for RealNet project. So that's short for artificial intelligence for real-world network infrastructure, which is a big European project where we try to bring AI support to such domains, right? So here on the right, you see an infographic about some of the things that we try to do in this project. So we have three domains: air traffic control, railway control, power grid control. And there are many specific features of these systems that they also have in common. For example, right, kind of currently this network infrastructure is really close to its maximum capacity. So using that smartly is very important. Sustainability is important. Multi-agent perspective is important. Safety and robustness is very important. Then there's also, right, important characteristics of the type of decisions that we make, right? So for example, we have to take account of unplanned events. And there's important characteristic that we want from our AI solutions. So we should be able to handle structured representations. We should be explainable and transparent. Also, right, going back from maybe from Diederik's talk, right, we need to be human-centered and so on. Okay, so within this project, how do we want to approach these problems? So what we really want to focus on is the interaction between the human operators, right? So currently, the current situation and also the future situations is that people, right, our human operators are in charge of these network infrastructures. So we want to support those operators. So what's very important is then the interaction between the human operator and the AI agent. And we can model that in different ways. So we can have situations where we have full AI-based control. So in this case, right, we have an AI that's operating autonomously, but there is a human supervisor that's maybe, right, auditing or supervising what this AI is doing and maybe able to intervene if something is going wrong. We might have co-learning scenarios where AI and human operator are jointly making decisions. And we might have full human control where a human operator is making all decisions and the AI is just providing the human operator with some, for example, recommendations or forecasts and so on. Okay. What are some core technical challenges that we need to solve to get there? So some of the challenges that we have is like, right, compared to training, let's say ChatGPT or similar models where you have these huge, right, online data sets with like kind of millions and millions of records, right? Here, how much data do we have on control of our power grid or train? Well, that's maybe, in the thousands of records, right? It's much, much smaller. These networks are very large scale, so we need scalable solutions that can, cope with whatever, hundreds of trains, for example. Um, Solutions need to be transparent and trustworthy. Um, we need, right, humans in the loop in the decision making. I mean, depending a little bit on, right, from the previous slide, like what type of interaction scenario we're focusing on. We typically have also many different types of objectives that might be prioritized in different ways. So we need some type of multi-objective decision making. It's important to focus on the interaction with the human operator. So not just, right, the AI choosing the optimal plan, but also how you communicate about this and how you maybe handle the human operator having their own preferences. And how do you handle this joint decision making? Um, so yeah, maybe kind of how this is kind of structured and what we're trying to do. So in the technical core of this problem, we have a work package on building fundamental AI building blocks, where specifically we focus on these two challenges of dealing with limited data by using knowledge-assisted AI. So right, going away from being purely data-driven, but combining data-driven learning with implicit or explicit human knowledge, and dealing with large scale by focusing on hierarchical decentralized decision making to kind of try to factor out these huge problems. Then we have also a task on improving transparency and trustworthiness. Then in work package 3, it's really about this interaction between the human operator and the AI systems. So you focus on here, right, is, okay, how do we make decisions with the human in the loop? And also, how do we do this joint and interactive? Then this is, right, kind of bookended by these two other work packages where we are defining a conceptual framework, use cases that we can use, right, to kind of validate whatever algorithms we develop in simulated scenarios that are somewhat close or representative of challenges faced in the real problems. And a pretty exhaustive evaluation, not just of technical performance, but also of performance in terms of safety and robustness, social, technical, decision quality, trustworthiness, and right, kind of, let's say, policy relevant issues like economics and regulation. All right, and there's many partners involved. So right, it includes industry, academic partners, research institutes, small, medium enterprises on kind of these diverse topics like AI itself, core AI, human-machine interaction, and those various application areas. Okay. So kind of to switch now from that very high-level overview to kind of two specific kind of technical problems that we have done. So in the rest of my talk, I want to talk about the following two projects. The one is on hierarchical decision-making for power network control. This was actually a project we did before the big European project started with a master student, and a currently ongoing project on learning augmented multi-agent path planning. So right here, the idea is that we combine planning techniques with a little bit of learning to improve it. So I'll go into all the details, obviously, later for that second one. So let's start with the first, right? Power network control. So what is it that actually needs to happen here? So there's this nice figure from this paper by Marot, which, by the way, describes a international challenge on developing AI solutions to running a power network. That was the 2022 edition, but there are also new editions coming up. So we have some environment, and this environment, right, consists of the power grid, right? That's important for us. So we have substations, those are the nodes in the graph, and then we have lines, those are the edges of the graph. So these are, right, the high voltage power lines that you see. And we also have right, various entities kind of connected to the network. So we can have generators, like maybe a wind plant or a nuclear plant, and we also have loads. So these are consumers of electricity, like right, perhaps residential areas or factories and so on. And right, at any given point in time, we can simulate some amount of electricity, power being generated, power being consumed, and then power being transmitted along the various lines. And now the problem here is that these lines have limited capacity. So I think the capacity here is always 100, so it's just kind of percentage of the maximum capacity. And we see that with the current pattern, there's actually a load here that exceeds the capacity. So it's 118, 18% above the capacity. So actually, this will generate a negative reward for us. And the real life situation that this reflects is that these lines can be a bit over capacity for a short time. That's not catastrophic. But as the power is higher than the capacity, those lines will heat up. And if they heat up, they expand. So these lines start to sag. And if they sag too much, they come too close to perhaps trees under it, for example, and they can start fires. So this needs to be remedied as soon as possible. Okay, exactly. Now there's different measures that can be taken. So there can be redispatching actions. And these are quite costly. So these are actions like, okay, maybe if we generate a bit more electricity close to here, for example, by firing up a coal power plant, right? And use a little bit less of the wind energy that's generated over here, perhaps this is solved, right? But that generates a lot of extra carbon emissions and it takes extra money. We don't really like to do that. You can also pay consumers to use less electricity. So maybe you have a contract with a big power plant that, right, you pay them some money to reduce their demand for a certain amount of time. It's also costly. So what's actually a much better alternative is what they call these actions that change the network topology. So one thing is you could take actually one power line offline, so you just don't use it at all. And kind of counterintuitively, that can sometimes reduce the load elsewhere in the network. And there's another thing we can do, which is node splitting. So actually the physical kind of node over here can be kind of split into two virtual nodes. The hardware infrastructure is there for that, so that that can be done kind of without cost, let's say. And that results in kind of a different network topology. And now if we do the physical calculations again to figure out, right, how will the power flow through this network, you see actually this resolves the issue, right? The load here is now 99, which is under 100, so everything is green, which also means we'll get a higher reward. So in this case, 0 instead of 1. So that's great. So that's what we focused on in this project, are these type of topological actions. Okay, what was our major challenge here? There was the scale or the size of the action space. So you can imagine, right, like if I can split, so right, this is a bit zoomed in version of a power grid. This is a specific power grid called the IEEE 14 bus network, which is kind of used as a kind of a standard example. And we see we again have like, right, these different substations, which sometimes have, for example, 6 loads connected to it, or 6 lines, nodes, and so on connected to it. So how many ways are there to reconfigure that? Well, there would be about 2 to the power 6, right? It's in the end, it's going to be a little bit less because we have some constraints that we also need to take into account. But that's the kind of order of magnitude. So if we can reconfigure each of these substations, in the end, we can have something like 23 million possible grid topologies, right? So that's way too huge to even start thinking about. However, kind of in practice, we also don't want to reconfigure every possible substation at the same time. So if we instead say, well, let's only reconfigure one substation at a time, then, right, depending on if that's a substation with lots of different connections or one with very few connections, you might get something between, oh, I don't have it here. I think it's between something like 3 to 26 possible configuration for a single substation that we can choose. So if you then add up those possibilities for all the different substations, you end up with 106 possible actions that can be taken. So these 106 possible actions are the sum of possible configurations for each of the substations. Right? Okay. Now, these 104 actions are still a pretty large action space. So now right, it was kind of our turn to kind of think about how do we want to approach it. Now, the first step was already taken by many of the approaches in this challenge, which was kind of at the very top, before deciding to do anything, decide if you need to do anything at all. So there's kind of a hard-coded rule in there which says, well, unless any of the lines is near a threshold, simply don't do anything. We can easily model this in the SMDP framework. And then, right, maybe our job starts, which is what do we now do? And what we wanted to do is kind of use a kind of hierarchical approach, where first we choose a substation. There are 7 possible substations that we can choose. And then for that chosen substation, we pick a configuration. So it's between 3 to 26 choices. And that prevents us from having to consider all 104 possibilities. Okay. And how do we then model this with RL policies? Well, first of all, we can define what our baseline is. So in our baseline, we just have what we call the greedy expert. So the greedy expert simulates for all 106 actions what the power flow will look like if that action would have been taken. So that's a very expensive rule. And then you just take the maximum. This is quite expensive because you have to evaluate all 106 scenarios. And it's actually also suboptimal because this is greedy. You just look kind of one step ahead, what will happen immediately as a consequence of that action, but it doesn't really take into account what will happen into further. So what can we do instead? We could do reinforcement learning in the native action space. So here, right, we have probably some neural network that's going to output the distribution over 106 actions. So, right, implicitly, this RL agent is going to also take into account, of course, future rewards, because that's how we train it. But then we can, right, try to use this type of hierarchical idea. So instead, what we could do is say, oh, instead, the reinforcement learner only picks the substation to change. And then perhaps we still have a greedy selector that chooses then the configuration of that one substation. So the benefit here is, right, from 106 actions, you go 2, 3 to 26 actions. That needs to be evaluated by your simulator. We can also have on both levels a reinforcement learning. So we both have a reinforcement learning that picks a high-level action, and then for that substation, between the possibilities in that substation, another reinforcement learner then picks the precise action to apply. All right. Then we tried training the RL agents of either the PPO or stochastic actor-critic algorithms. The state representation for these algorithms consists of the current configuration of the network, the power that's currently generated by each generator, consumed by each load, and transmitted by each line. And furthermore, per line, we have the load as a percentage of the maximum capacity, and also the number of time steps that the line already has an overflow, because, right, this was related to what I said at the beginning. Going over maximum capacity for 1 or 2 time steps is fine, but it's very important to know that it's getting more and more critical the longer this situation persists. So that's why it's important to know that. And then we just use feed-forward neural networks that can select any of the possible actions. If we have these hierarchical scenarios where already a substation was chosen, all of the configurations that belong to other substations are simply masked out, so they cannot be chosen by the policy. All right. So then let's go to the results that we had. On the left here, we see the results on the train scenarios. And right on the horizontal axis, we just have the training time. And on the vertical axis, we then have the mean return of the episodes. And we see that the PPO-based methods seem to do better than the SAC-based methods. And this hierarchical approach, where we learn at both levels, we got very unstable results. So you see this blue kind of shaded area, which represents here the standard deviation. It's huge. right? So sometimes it works terribly and sometimes it works great. Okay. What we then did is, these were, I think, 10, with 10 different random initializations, we trained each model. That's how we also get these intervals. We then, each of those individual models, we tested on a validation set, and then the best one we evaluated on a test set. So now here, this PPO hierarchical, which had this, either it worked great or it works terribly. This is kind of the great one, right? It's shown here, and the same for all the other methods. I also compared to this greedy approach. So on this unseen test scenario, we are showing for each of those different methods is the mean episode length. So the episode ends if essentially something goes wrong, right? So if any of the lines is overloaded for too long, kind of the simulation is cut short. So I want this to be as high as possible. So that's what's shown in the orange bars. We see actually that there is a big potential for these learning-based methods, right? Actually, all of those learning-based methods do better than this simple greedy baseline. Yeah, within those results, we also see that PPO hierarchical performs best. What we also measured here is how often do these methods actually need to intervene. So in blue is the number of topological actions selected. And we'd like this to be low. We'd like to not, like every time step, have to reconfigure one of the substations. So this is not explicitly encoded in the reward function, for example. So this is not kind of formally an objective, but it's still something we wanted to measure and just see, right, how often do these methods happen to take actions. And here, yeah, we see that what tends to happen is that in these actions chosen in the native action spaces actually leads to more interventions than right. So this is just native, just means you're picking from all of the 104 possibilities, and the strategies where you first put the substation and then the configuration for that substation, you tend to make less interventions. And actually, the greedy heuristic makes the least interventions of all. Right. So this between the learned algorithms is kind of seems to favor those hierarchical approaches. Okay. So what are takeaways from this part? It's that hierarchical decision making seems at least as good as this decision making in the native action space while being faster. That's not something that I showed in the diagrams, that's in the paper. And you can also imagine that as you scale up from this super tiny 14 bus network to, let's say, the whole high voltage power grid of the Netherlands, for example, yeah, that is important, the scaling behavior. So their hierarchical approach is really very important. Yeah, this also shows, right, that kind of reinforcement learning does have potential to help in these cases. Yeah, but for future work, here we used simple feed-forward neural network, which is actually, yeah, not maybe really right tool for the job because it doesn't really allow sharing data between similar parts of the network, right? There's nothing that encodes, hey, this substation fulfills a very similar role to that substation in its local area, for example. And it also doesn't allow generalizing between this network and another network, right? Perhaps I'm adding another substation and I would like my policy to still be applicable in this new network, or I want to have a network trained in one country to also be applicable, or at least a good initialization for another country. All of that you cannot do with feed-forward neural network that don't understand the topology of the network. Okay. Before I go to the next topic, I just want to say that within the consortium, there's a lot of work, right? Kind of within this AI for RealNet project that goes further. So yeah, here's a couple of examples that would be very interesting to take also a closer look at. But then I would like to continue to the second study that I want to talk about, which is this idea of learning augmented multi-agent pathfinding. So this is a current work in progress. I only have some preliminary results. I'm quite excited about it, so I'd like to tell you a little bit about it. And this is in one of the other domains. So this is in the train planning scenario. And again, here we have another online challenge that we consider within the project as a kind of virtual counterpoint to the real world challenge, which is called Flatland Challenge. So we have kind of simulated worlds like this one, where there are different cities and stations and train depots and so on. And now the problem is, right, you have a bunch of trains, so it's a multi-agent challenge. And all these agents have a starting point and an end point where you want to be at a certain time. And of course, you want to get there without colliding with any of the other trains. So what are the challenges here? We need to make decisions at scale, right? We might have many, many agents. We might have very big maps. We also have to handle stochastic breakdowns. So trains can break down, and while they're broken down, of course, that track cannot be used by other trains either. And that means, right, that it's very hard to use conventional optimization techniques, since these breakdowns are stochastic. And right, the hope is that reinforcement learning is actually better to handle those stochastic events. Now, there's some disappointing news about that, which is if we look again at previous iterations of this challenge, we can see, right, there is some analysis from a kind of retrospective paper about this challenge, that if we look at an OR strategy that was proposed by one of the competitors, and RL strategies that were proposed by other competitors, OR operations research, so that's more based on classical planning and optimization tools. And we see how well each of these methods do as the scenarios get more complicated, so more agents on a larger grid. We see that actually these reinforcement learning methods don't do so well at all at this scaling. So, right, and that kind of prompted us, well, okay, so, right, of course, RL agents are maybe starting from scratch, and OR methods, right, have for decades been optimized for example, multi-agent pathfinding problems. So perhaps there's a good reason for them being very strong. And now maybe our question is, can we kind of leverage those, right, insights that help us to do so on this problem to improve learning techniques? And maybe also the other way around, starting out thinking from this planning or optimization perspective, can we add a little bit of learning to those type of methods to make them even better? All right. Now, so when we start thinking about that, the first question is, okay, which type of planning approach do we even want to start from, right? So of course, there's planning approaches that are optimal, right? So something, for example, for multi-agent planning, there's conflict-based search. If you don't know what it is, that doesn't matter. But that's an optimal method that doesn't really scale beyond a dozen or so agents. So instead, right, what's used if you go to a larger scale are heuristic planners that can scale to very large sizes, but right, generally can't guarantee optimal performance. And we look specifically at one such heuristic planner, which is prioritized planning. And if you don't know what that is, the short answer is you prioritize the agents, so you put them in some order, and then you just solve a single agent path planning problem for only the first agent. So it just takes the shortest path for itself, greedily. And then the second agent, you say, okay, given that that's the path that the first agent takes, what's the best path that you can take that doesn't conflict with the first one, right? So yeah, as you go on, the space becomes more constrained, and the earlier agents don't at all take into account that there will be someone coming after them. So that's what makes this suboptimal. And our questions are now, if we somehow include some kind of prioritized planning in reinforcement learning, does that help RL? But also the other way around, does adding a bit of learning, can that be better than using the pure original prioritized planning? Now, I claimed that prioritized planning was suboptimal. I can also show an example. So here we had kind of, like, let's say, a bit of a pathological construction with an agent 1 that starts here and wants to go to its goal, and an agent 2 that starts here and wants to go to its goal. And now if we do prioritized planning, and we prioritize agent 1 because it has the number 1, it will take the shortest route. That's like this. And then agent 2 doesn't have a choice but to kind of go around agent 1. So it's all the way around like this, which means that this agent 2 has a pretty high cost. So if we look at the make span, which is just the max of these two costs, or the flow time, which is just the sum of these two costs, you get numbers that are actually higher than they need to be. So if the if it was the other way around, agent 1 would take the detour, agent 2 would go like that, you'd actually end up with, I think, this one lower and that one 2 lower or something like this. So, then the question is, can we use learning to somehow improve this? So the angle that we decided to take when looking at this is, hey, can we assign different costs to the segments? Of course, each segment has a cost. That's simply how long, what's the distance of this segment, and that's what we try to minimize in the prioritized planning. But maybe we can adjust it a little bit. Maybe we can say, no, actually, treat this edge as if it were a little bit longer. So you'd maybe avoid that edge if possible. And what we hope to achieve is that this then encourages prioritized planning to avoid such especially busy segments. And in the future, we don't only want to do this assignment of costs to the segment, but also assigning priorities to the trains. Then that changes the planning instance that's given to the planning module, right? So these are the learned components. This is just the kind of algorithmic component, and that will then yield some kind of trajectory, right? And now we want to change the parameters of one or both of these boxes in such a way that we get good trajectories out. Then the question is, what's a good trajectory? So there's at least two ways in which we could do that. We could say, well, we have expert trajectories. So these are, for example, really the optimal trajectories. And we want the trajectories coming out of this whole pipeline to just be close to the optimal ones. Obvious weaknesses, you need to have the optimal ones in the first place. Or we directly maximize some reward functions, so it would be truly in the RL setting. Okay, the technical challenge is then, right, if we want to learn by backpropagation, how most deep learning works, is that we have to go through this planning algorithm. And that, of course, doesn't have gradients, since it is, right, we change the parameters here a little bit. In most cases, probably there's not going to be a different optimal plan coming out of the planner. So we use a technique for relaxing the planning module so that we do get some kind of, let's say, approximate gradients that we can then use to adjust the parameters over here. Okay, is this effective? Well, on this very small example, yes, this is effective. What we end up learning is a parameterization that gives a slightly higher cost to the edges over here, a slightly lower cost to the edges over here, which means that agent 1 is going to take this route, agent 2 is going to make this route, and then by the original objective, actually we do a little bit better. The make span is lower and the flow time is lower than they were before. Okay. Beyond this very anecdotal example, we're currently in the process of running this on benchmark problems, and I only have results for this one specific benchmark problem, and obviously our goal is to do more, right? So that's currently underway. So right, this is just a kind of simple grid world where these black obstacles need to be avoided, and then we have run that with either 50 agents, 75 or 100 agents, and we see a percentage over some lower bound of the distance achieved by the final plans. And we see that in all these scenarios, the prioritized planning with the learned weights outperforms, but not by a huge margin, the original prioritized planning. Now, what we hypothesize is that this is an environment where you still have it's still quite easy to avoid each other because you have these rather big rooms and rather wide corridors. So we think this difference will be bigger in more like maze-like environments where you have narrow corridors that are maybe more like this railway networks. But it's currently, we're currently evaluating that. And just as an example, We show also the learned weights over here, which, where you can see that maybe it's a bit hard to see probably from a distance, but the higher weights, so the yellow ones, tend to be the kind of isolated stretches that connect, let's say, these bigger rooms. And within the bigger rooms, you have the lower costs. So those are the blue edges, which indicates that we are trying to induce the agents to not use these kind of more critical connections that might also be very important for others if there is a good alternative. All right, so our takeaway here is, if we combine learning with this implicit knowledge from this prioritized planning heuristic, we can actually get better performance out of this heuristic. And in the future, as I already indicated, we want to learn also the priorities, and we also want to learn directly from the rewards. So the results here were all in the imitation learning setting where we learn decisions by trying to copy the optimal solutions. Okay, if we take a step back and go kind of all the way back to the overall problem of applying reinforcement learning to real world scenarios, there are still kind of these big challenges, that we aim to address within the project on collaboration, trustworthiness, and scalability. And we have addressed a small fraction of the challenges here. And those are challenges that we then want to further study within this EU project. So, the questions about using an RL agent as an assistant. So I think from the RL perspective, what's very interesting there is the human operator is now going to choose possibly different actions than the agent would take. But if you have an agent that's trained to act autonomously, what type of problems does that create? So, for example, the human operator might steer the agent to states that the agent would never visit by itself, so it might not be sufficiently trained on those states. So how can we make the agent robust to that? All right. I won't repeat the rest in the interest of time. Then I'll just go to my last slide, where I would like to thank, I'd like to thank all of you for your attention. And I, in particular, also want to thank my collaborators on these projects. So that's Lazé and Jan on the first project that we discussed, and Marius on the second project. And then I'd love to answer any questions that you might have. Thank you.
Oh, no, I won't. No. Thank you. Asking about this power systems example, I would imagine that when you switch lines, you get different transient responses. Does your reinforcement learning approach take these transient responses into account? Because what we saw the other week in Spain was a blackout driven by transients which were undesirable.
I don't think it does. So this is an obvious simplification of the problem, right? I mean, it is like it's not something kind of that we naively cooked up. This is created. I think the driving force behind it is the RTE, which is the grid operator of France. But I think the only thing that this simulator takes into account is let's say the steady state that you get when you have this or that.
Okay. And if I may follow up on that, have you compared your reinforcement learning solution to some optimization-based approaches? Because that is the other big trend which is going on these kind of problems, to code up mixed integer optimization problems and then solve it with deterministic algorithms.
Yeah, this was a rather, this was a master student project, so it was kind of limited in scope. I can't speak for what others have done in the consortium, but my guess would be that some of these papers do kind of more fully take that into account. And also probably, there's a reference here to the retrospective paper on the challenge there. That my money would be on that. That would also, puts the different approaches here in context.
Thank you.
My question relates also to the previous talk. So I'm curious now that you have this cool model system you can train RL on, and they're very related to the real world, either grid systems, which can break down, or train systems, which, as we know, the Netherlands can also break down. I think 2 years ago, the whole train network was just dead for a day or something. So are these model systems kind of rich enough to model that kind of very rare but very catastrophic result of policies at some point?
Yeah, I mean, the aim is that they do so, because those type of issues are a kind of explicit focus point within the bigger EU project. Now, I myself am not involved in designing those virtual environments, but we have partners that are train companies and that are power grid companies. So it would make sense, right, that they will want to get something out that is useful for them in those ways. And right, when I was talking about this exhaustive evaluation, then zooming in on like what are the kind of catastrophic events that can happen, that is very important to the success of the project. So the goal is yes. In how far they are representative, very hard to say.
Yeah. Great, thank you.
Like, for example, right, one goal of the project is also to kind of adversarially evaluate. So like, kind of what's the worst case, right? For example, if one of the power lines is down, what's the worst case that could happen? And then what does our method do, right? So kind of a real stress test. You can either think of, well, whatever happens, we want to be prepared, but also, yeah, from the perspective of possible sabotage or something like this, right? If I were to try to attack the physical infrastructure, if someone were to try to attack that, are there, let's say, obvious weak spots for them to find? And is there something we can do about it?